Welcome to another video from Lockdown Electronics with me, Bill, and this time we're going to take a look at modulation, in particular CW or Morse code modulation, amplitude modulation, and single and double sideband, which is a derivative of amplitude modulation. Now, one of the great things about modern transceivers, and even for that matter humble USB dongles that you can attach software defined radio to, they usually come with some kind of waterfall display, which essentially produces a history of the signals that they've been copying across a spread of spectrum. And that can be quite handy if you're wanting to look across a band for activity, or you're searching for stations. It's a very handy feature. In the past, these things were called pan adapters, and they were usually add-ons, and sometimes quite expensive add-ons to radios. But these days, waterfall displays are a very common thing, and I guess in a way it's a form of spectrum analyzer. So I thought it might be good to have a look at modulation, have a look at what we're actually seeing on those displays, and see how we can interpret it. And hopefully, if you're somebody who's perhaps working towards getting your amateur radio license, or just want a bit of revision on modulation, hopefully the information here is going to prove useful to you. So let's start by having a look at some signals generated here in the lab, just using a signal generator. Okay, I'm just going to start by having a look at some different types of modulation produced from a signal generator, and then we'll go on to look at some examples in the real world. And so the first most simplest sort, of course, is CW, or carrier wave. And if I put on a signal there, you can see we get a pronounced peak, about 7.1 megahertz in this case, from the signal generator, and a very narrow bandwidth. And by the information is modulated onto that signal by simply turning the transmission on and off. We'll have a look at that on the waterfall display of a HF transceiver in a while. Amplitude modulation then requires encoding the signal with usually voice, and that's done by varying the amplitude. So we'll turn on amplitude modulation, and the first thing that you notice is we get two more prominent peaks. Those are the upper and the lower sidebands. I'm modulating this carrier wave with currently 2 kilohertz, so you'd expect those two sidebands to be 2 kilohertz either side of the carrier wave, and indeed they are, since each division on the display there is about 2 kilohertz. Now if I increase the modulation frequency, you can see that the sidebands move away, so we're now at 6 kilohertz, and depending on the frequency you get a different position for each of the sidebands. The important thing to notice, though, of course, they are completely symmetrical, and so the information in the upper sideband doesn't tell you any more than the information in the lower sideband, and that's why single sideband is such a handy method for transmitting. It's harder to produce, but we only end up transmitting one sideband, and we don't even bother with the carrier wave. So we can simulate that on the signal generator. I do have the ability here to transmit to generate double sideband. So that's a double sideband, and we're bang on 7.1 there, and you can see all it's transmitting is 7.1 kilohertz, and we're modulating that with 100 hertz at the moment. So let's up that to 1 kilohertz there. So that's 1 kilohertz, and so we've now got the upper and the lower sideband just about 1 kilohertz apart. So that's double sideband. And I don't have the ability on the signal generator to produce single sideband, but single sideband essentially would just be one of those peaks. So the carrier now at 7.1 has been completely suppressed. So if I just pop back onto AM, if I can, there we go, we're back onto AM, and so we get the pronounced carrier. And if I modulate that at 1 kilohertz there. You get a pretty good idea of what it looks like with the 1 kilohertz modulation. So we'll just nip back to the double sideband there, so we get 2 sidebands, and if we pop back to AM, we essentially insert the carrier. Okay, so that's AM and double sideband. Let's now have a look at some of those plots on the oscilloscope. Okay, I fully appreciate that not everybody's got access to an spectrum analyzer, although I have to say the Tiny SA is very good and certainly capable of doing some of the things you've just seen on my slightly more expensive version. So here's the carrier wave displayed on the oscilloscope in the time domain, and as you'd expect, it's a sine wave. If we now modulate that with 1 kilohertz at AM, we get a display that looks a little bit like that. And if we increase the time base to say something like that, and I'm just going to pause it so you can see the shape of the waveform, we've now got the classic modulation envelope where the amplitude of the signal is being modulated at the frequency of the modulation frequency, which in this case is 1 kilohertz, hence the envelopes going along there, and the sort of shading in the middle is actually the carrier wave frequency. So that's how it appears in the time domain. Now if you've got a scope with fast Fourier transform, you can put your FFT on and see what happens in FFT. Now you need to just play with the display a little bit, so I'm going to center up on 7.1 megahertz, so just bear with me while I do that. This knob's a little on the, should we say, lively side. So there's 7.1 megahertz, and we're at 1 megahertz per division, so I'm going to reduce that now considerably down to 100 kilohertz, 20 kilohertz, 10 kilohertz, and 2 kilohertz. Actually, I'm going to go back to 5 there, and you can certainly see that we've got a signal, but you can't see any sidebands. So a good trick here is to alter the time base of the scope a little bit, and you suddenly discover that if you give it a bit more information. Okay, so there we are at about 500 microseconds. You can actually see the carrier wave, and you can see the 2 side bands. So if I just go onto the double sideband, we should now lose the carrier. Yeah, there you go. So you've now got your 2 peaks either side, which are the up and the lower sideband, and we'll go back to AM, and I'll just show you that your FFT is probably capable of doing quite a lot. Let's now increase the modulation frequency to 2 kilohertz and give the FFT chime to calculate 3 kilohertz, and you can see the sidebands are moving apart. Remember that the scope here, of course, is calculating the frequency domain plot from the time domain plot, so there's a great deal going on in terms of mathematics here. So yeah, your FFT is capable of showing that up if you want to see it in both time and frequency domain. Okay, let's now have a look at some real world signals. Okay, here I am on the 20 meter emitter band, right at the bottom end of the CW section, and I've got a strong CW transmission there. I've deliberately put it slightly left of centre because I want to pause it when I do the display, puts a line down the centre. But if I just hold it, it's almost possible to actually make out the dots and dashes in the waterfall display. If you were to adjust the speed of the waterfall display, you could potentially recognise the characters visually rather than audibly. But as you can see, we're at 10 kilohertz either way again, and that transmission is incredibly narrow and clearly very, very spectrum efficient. Here is the Icom 7300 tuned to a medium wave broadcast band transmission. It's an AM transmission. You can clearly see in the centre the very bright trace produced by the carrier wave, and then to the left the lower sideband, to the right the upper sideband. And what I'll do is just pause the display for a moment, like so, and you can see there's a symmetry between left and right hand side. They're mirror images, symmetrical, but you've got the same information in the lower and in the upper sideband. Just to show that's not a fluke, we'll let it carry on receiving for a moment or two and pause it again, and you can see you've got obvious symmetry there, etc. So the thing to note there is I've got 20 kilohertz span set, so I'm tuned to exactly 1.17 megahertz, and the signal is probably occupying, well, just over 6 divisions, plus or minus 6 divisions, so 12 divisions altogether. So that's 20k. It's probably occupying maybe 14-15 kilohertz, and that's a relatively lo-fi medium wave transmission. Okay, here's the medium wave broadcast station that was on 1.17 megahertz, viewed on the spectrum analyzer, and I've currently got the bandwidth set to 3 kilohertz, and you can see we've clearly got a strong signal centered on 1.17. Let's now reduce the bandwidth. That's at 1 kilohertz, and if I go down to 300 hertz, straight away you can start to see the carrier there centered on 1.17 and some stuff going on either side. If I go down to 100 hertz, you get a bit more detail. If I go much below that, that's 30 hertz, starts to impact on the sweep speed. So I'm going to go back to 100 hertz because that's plenty good enough. So you can see sidebands there, but the really easy way to pick that out is to add an additional trace. So let's add an additional trace, and we'll put that onto max hold. So the blue trace then is the maximums that it's picking up, and you can see pretty clearly now, particularly if I turn off the main trace for a moment, you can see pretty clearly there we've got two fairly identical sidebands going on. Just going to change the bandwidth to 30 hertz there, and that'll take a moment or two to build up, but you can certainly see mirror image symmetry either side of the carrier wave, and drops off fairly steeply once it gets to about 3 and a bit divisions. So the total span width there then is 20 kilohertz, so probably about 15 kilohertz of that is where the signal is. And certainly for an amplitude modulated signal, you can see pretty clearly that we have the same information in both the upper and the lower sideband. Okay, now I'm tuned to 5.505 megahertz, and settings are identical apart from the fact that I'm set to receive in upper sideband where I was in AM before, and we've got a signal here, and the reason I've picked this one is this is the the aeronautical weather information. If I turn it up for a moment,
the 18th at 0600 until the 19th at 1200. Wind variable.
So it's an aeronautical transmission, so it's being transmitted on upper sideband. And first thing to note is that in between the words, if I just pause that for a moment, you can see there are some lines there where there is no signal, which is a nice example of how when you're not in between the speech, there's actually nothing being radiated off a single sideband signal. So we'll let it run again, and if I just wait till there's some words, if I can catch it when she's speaking. Yeah, there you go. So, and the bulk of the transmission is in well. That again, we've got exactly the same spread, so plus or minus 10 kilohertz. So the bulk of the transmission is within 2 or 3 kilohertz there, and it's obviously more than readable. Interestingly, probably easier for me.
060 degrees, 5 knots. Wind varying between 010 degrees and 160 degrees.
Now, to my English ears, although that's an automated transmission, obviously originally the words were spoken by a person, and to my practiced British ears, I can hear a hint of Irish accent in that voice, which isn't surprising because it's being transmitted from Shannon in the west of Ireland. It's the transmission that's used by transatlantic flights for picking up the weather information, and there's sufficient information in that fairly narrow spectrum for me still be able to recognise a little bit of an accent. And again, I'm just going to pause that for a second. Lovely example there of absolutely nothing being transmitted in between those speech peaks. So there's an example of why single sideband is such an efficient method of transmission, and I've picked the Shannon Volmet frequency because it's a strong and reliable signal that allows me to video it and capture it. Obviously some of the amateur sideband frequencies aren't always in use. Here then is the spectrum analyzer with the same 20 kilohertz span, but this time centered on 5.505 megahertz, the Shannon Volmet frequency. And you can see we have got a signal there. It intermittently appears, which is to be expected as this is a single sideband signal. So let's now add an additional trace to that, and let's make it a max hold, and hopefully you're going to be seeing the signal sort of growing out of the noise there. What I'm actually going to do is I'm just going to change the scale to division to 5 dB, so it's a little bit hopefully a little bit more obvious. Okay, there we go. So now what I'm going to do is just turn off the continue updating trace, and what we can see here now is just the max hold trace. So we've got exactly on 5.505, as you can see, pretty much no carrier whatsoever, and all the energy is concentrated on the high frequency side of 5.505. In other words, all we've got there is the upper sideband, and you can see the vast majority of the upper sideband is within about just slightly over 3 kilohertz. You've got 2 kilohertz per division on that display. So that's a nice example of single sideband. And if I now put the original trace back on, and what I'm going to do here is we'll just turn off the high peak hold, so you can see, although it's less obvious there, that in between the words there's pretty much no energy being radiated at all. So nice example then of an upper sideband signal. Okay, I'm back on 20 meters again, and here's a station calling CQ on upper sideband, and nice narrow transmission there, and I'll wait for him to transmit again, and I'll turn the volume up so you can hear that the audio is perfectly readable and makes complete sense. Oh, there we go. So there's an example of amateur single sideband. Okay, here's a quick look at why it's quite important to be in control of your bandwidth on the spectrum. I've now got the spectrum analyzer centered on 5.4035 kilohertz, which is in the 60-meter amateur band here in the UK, and I'm just taking an RF sample off the output of the transmitter, which is running into a dummy load. So I'm just going to transmit 1, 2, 3, 4, 5 test, and you can see we're getting a signal there. So what I'm now going to do is add an additional trace, and we'll go for max hold. 1, 2, 3, 4, 5, 6. Okay, and so what you can see there is we've got single sideband signal starting at 403.5 and occupying 3 kilohertz up to 6.5, where it drops away again, and that's pretty good really. I'll just put a couple of lines on there now for you to see. So the band itself extends from 403.5 to 406.5, so it's quite important when operating up a sideband that I set my transmitter output to 403.5, which means that all of my 3 kilohertz of single sideband is contained within that that sort of bandlet, that mini band. Okay, hopefully that makes a bit of sense for you. Okay, well, that's modulation. Certainly a little bit about modulation. It's quite a complicated topic. We've not looked at some of the data mode modulations, frequency and phase modulation, for instance, and there's others as well. However, maybe that's a topic for a future video. In the meantime, hopefully it's been some use to you, maybe for revision if you're working towards amateur radio exam of some kind, or maybe if you're just interested in how information gets put onto radio waves. Thanks very much for watching. If you've enjoyed it, please click the thumbs up. Either way, if you've not subscribed, would please encourage you to do that. Also, if you could let people know about the channel, that would help me as well, and we look forward to seeing you on the next video.